Hi, welcome to video 8.38 part 2, more trig integrals. These will be formulas for sine squared x and cos squared x.
What if you just have sine or cos to an odd? But what happens if both the exponents are even, or if you just have a sine or a cos to an even? And what we talked about will not work. Well, we are going to use these two, what I call the square trig identities. But they're basically, you're taking the cosine of a double angle and isolating. So you will need to remember these formulas. Sine squared x is 1 minus cosine 2x all over 2. Cos squared x is 1 plus cosine 2x all over 2. And here's where the formula comes from. If you take the formulas for the cosine of a double angle, you will have cos squared minus sine squared, which of course if you replace cos squared by 1 minus sine squared becomes 1 minus 2 sine squared. Or vice versa, you could leave the cos squared alone and replace the sine squared by 1 minus cos squared, and it would give you 2 cos squared minus 1. So if I take this version here, cosine 2x equals 1 minus sine squared x, and I subtract 1 from both sides and divide both sides by negative 2, you see that I will get that formula that we just talked about up here, 1 minus cos 2x over 2. Same thing, if I take cosine 2x equals this last version and I isolate the cos squared x, I will get cos squared x is 1 plus cosine 2x over 2. Okay. All right, so if we just have sine to the fourth, that would be the square of sine squared. I do want to emphasize, very important, that you cosine of 2x and cosine squared of x are not the same thing, so be careful that you don't write it so that you can't tell whether the 2 is a coefficient of x or an exponent. Just be careful. So sine to the fourth is the square of sine squared, and now we're back to our Pythagorean identities. Sine squared x can be rewritten as 1 minus cosine 2x over 2, and then at this point you're going to expand that. You have your square your numerator over the square your denominator, and then you expand your numerator, square, double product, square, and then, my friends, it happens again. You have another cos squared of an angle, which is 1 plus cos of double that angle over 2. Okay, so when I multiply through, that'll give me plus a half cosine x to the cosine 4x. You have 1 plus a half is 1.5 or 3 halves. You have your negative 2 cos x. So you have cos 2x. So you have cos 2x, you have the 2 here, and basically you have everything you need because there's your u is 2x, your du is u. And then the last term is plus 1/2 integral cosine of 4x dx. Now, of course, what you're going to do here is you're going to let u equal the angle, which will be 4x, and then you'll take the derivative of that, which is 4, introduce, counteract with a quarter. So you should end up with 1/4 times 3 halves x minus, and of course now you're looking at the integral of cosine u du, which will be negative the sine of u. So negative is here. The negative comes from here, and then the integral of this is sine 2x. Then this becomes 1/8, and when you integrate cosine, let's say v dv, you get sine v, which is sine of 4x plus c. And of course you could distribute this through if you needed to for some reason. Another way to approach this problem is I could say, okay, sine squared is 1 minus cos squared, multiply through, I have cosine to the fourth minus cosine to the sixth. Now this is a little creative. So here you could say, well, isn't that the square of cosine squared x? Well, cosine squared is 1 plus cosine of the double angle over 2 minus the cube of cos squared x. So again, you're cubing that same thing, and then you could go from there. Not a very pretty way of doing it. It would eventually work.